On December 19, 2007, a powerful explosion and fire occurred at T2 Laboratories, a small chemical producer in Jacksonville, Florida. The blast killed and injured workers, destroyed T2 Laboratories, and extensively damaged 4 nearby businesses. Windows blew into offices, striking workers with flying glass.
The explosion at T2 Laboratories is one of several accidents that the CSB has investigated caused by runaway chemical reactions. Accidents resulting from reactive hazards occur too frequently and often have serious consequences.
Behind me on this concrete pad, there used to stand a structure some 50 feet high that had a reactor vessel in it, in which the company that operated here, T2 Laboratories Incorporated, manufactured a chemical known as methylcyclopentadienyl manganese tricarbonyl, or MCMT for short. The entire structure and reactor vessel were blown away in the explosion.
T2 produced MCMT, a gasoline additive, in batches using a 2,500-gallon reactor. An operator controlled the process with a computerized system in a nearby control room. In the first step, liquid chemicals and sodium metal were loaded into the reactor, heated, and then mixed with an agitator. The reaction produced hydrogen, which was vented to the atmosphere. In normal operations, when the temperature reached 300 degrees Fahrenheit, the operator would turn off the heating system. But because this reaction was exothermic, or heat-producing, the temperature inside the reactor would continue to rise. At 360 degrees, operators would begin to periodically fill the reactor's cooling jacket with water. As the water boiled, heat was removed, controlling the temperature. However, on the day of the accident, the CSB found that the operator tried to cool the reactor as usual, but the cooling system likely malfunctioned, perhaps due to a blockage in the water supply piping or a valve failure. The temperature and pressure inside the reactor began to rise uncontrollably in a runaway chemical reaction. T2's co-owners returned to the plant after a worker called to report the cooling problem. While one owner searched for the plant mechanic, the other went to the control room. Concerned about a possible fire, he warned employees to move away from the reactor. Inside the reactor, the pressure was still increasing, reaching 400 pounds per square inch and bursting the rupture disc. Witnesses heard a sound like a jet engine as high-pressure gas began to vent from the reactor. But it was too late. Within 10 seconds, there was a massive explosion, equivalent to about 1,400 pounds of TNT. The blast damaged buildings over 1,500 feet away. Debris rocketed up to a mile. The co-owner and the operator in the control room were killed. 2 operators further away died from flying debris. 32 other people were injured, including 28 at nearby businesses.
This facility housed multiple types of chemicals. That was a kind of a mass storage of everything you can think of, and it was all mixed together and it was all burning together. And for our perspective from the hazardous material side, it makes kind of a worst-case scenario.
Damage from the explosion was so severe, 4 nearby buildings were condemned.
My office personnel heard a whistling sound in the area, and as they looked out the window, they saw an orange glow, which was the blast coming off of the explosion, and it came to our offices, and it blew in all the windows in our office trailers. Immediately, it was a shock or a surprise, and then all of us were shaken afterward.
In 2002, the CSB completed a study on reactive chemical hazards. The study identified 167 serious accidents involving uncontrolled chemical reactions between 1980 and 2001, causing 108 deaths and hundreds of millions of dollars in property damage.
When mixing chemicals that have an exothermic reaction, you need to be aware of the amount of energy that could be released by the reaction to prevent vessels from bursting like the one that happened here.
T2 developed its MCMT process using a 1-liter reactor. The company then scaled up the process directly to full production volume in the 2,500-gallon reactor. After 41 batches, T2 increased the batch size further by 1/3. As the scale of the reaction increased, effective cooling became ever more difficult. During 175 production runs making MCMT, T2 periodically experienced problems, such as unexpected temperature increases, but the company never fully investigated the causes. And T2 had only equipped the reactor with a simple cooling system using city water. When the system malfunctioned, there was no backup cooling immediately available to control the reaction.
The most important thing to managing reactive chemistry hazards is that you have to have a thorough and complete understanding of your chemistry under design conditions and also under all foreseeable abnormal conditions.
The CSB has noted that to prevent reactive chemical accidents, companies should identify and thoroughly evaluate reactive hazards in their processes, implement appropriate emergency pressure relief systems and other design safeguards, develop effective operating procedures and training programs, and carefully manage any changes to existing processes, and plan for possible accidents, including evacuation drills and emergency response exercises. Although T2's owners had undergraduate degrees in chemistry and chemical engineering and experience in the chemical industry, neither had been trained on how to recognize or control reactive hazards.
A large portion of the incidents have occurred because the people who are actually running the process were not aware either of the existence of the reactive chemistry hazard or of the potential magnitude of the consequences associated with that chemical reaction hazard. So a lot of the problem, I think, is education and awareness.
The board noted that multiple sources of information are available on how to control reactive hazards, including publications from the Center for Chemical Process Safety, the Design Institute for Emergency Relief Systems, and the UK Health and Safety Executive. Following the T2 investigation, the CSB recommended that the American Institute of Chemical Engineers work to incorporate education about reactive hazards into college-level chemical engineering curricula.
Reactive chemical hazards continue to be a too frequent cause of chemical accidents. Improved industry practices and increased education will help prevent these tragedies. Thank you for watching this CSB safety video.